Assalamualaikum warahmatullahi wabarakatuh. My name is FATIN AFIQAH binti ZAINALABIDin, matrix number 229117. Today, I will be presenting the video of presentation for assignment 2 solving engineering problem using dimensional analysis. In this short presentation, I will explain how we can use dimensional analysis, specifically the Buckham-P theorem, to simplify and better understand convective heat transfer from a heat flat surface to flowing fluid. This concept is crucial in many thermal systems, from heat exchanger to electronic cooling, where efficient heat transfer is essential for performance and reliability. Transfer is a key process in thermal system essential for the performance of equipment such as heat exchanger, electronic cooling system, and industrial heater. In many applications, heat is a transfer from a solid surface to a fluid through convection, influenced by a factor like fluid velocity, surface geometry, temperature difference, and fluid properties. Effective heat transfer is a fundamental process in many thermal systems, such as heat exchanger, electronic cooling device, and industrial heater. In our case, we are looking at a fluid like air or water flowing steadily over a flat heated surface. The heat is transferred by forced convection, which is influenced by both fluid motion and material properties. Understanding this process is essential for designing systems that are both efficient and reliable. Key variable in convective heat transfer. The performance of heat transfer in this system depends on several key physical variables. The fluid velocity affects the boundaries layer thickness. The surface length provides a characteristic scale. Fluid properties like density and viscosity determine how the fluid flows, while the specific heat and thermal conductivity influence the fluid ability to absorb and conduct heat. Finally, the temperature difference between the surface and the fluid derives as the heat transfer. Analysis. To simplify the analysis, we apply the Buckham-P theorem. We start with 7 variables involving 4 fundamental dimensions: mass, length, time, and temperature. This means we can reduce the system to 3-dimensional group. This includes the Reynolds number, which tells us about the flow rate, and Perrot number, which compares thermal and momentum diffusivity, and the Knox number, which represents the efficiency of convective heat transfer. This group makes it easier to analyze, compare, and design thermal systems without solving complex equations every time. Each dimensionless group we derive play a key role in engineering design. The Reynolds number tells us whether the flow is a laminar or turbulent. Turbulent flow enhances mixing and increases the heat transfer, while laminar flow is more stable but less efficient. The Perrot number compares how quickly momentum and heat spread through the fluid. For example, oil have a high Perrot number, meaning heat stays near the surface longer. Finally, the Knox number shows how effective convection is compared to conduction. A higher Knox number means better heat transfer. This group helps engineers choose fluid optimized phase and scale lab tests to real systems, ensuring performance while reducing number used and cost. Real-world example of using dimensionless group is the automotive radiator design. Radiator must be cooled and engine effectively under various driving conditions. At low fluid or air velocities, the Reynolds number is low, causing laminar flow, which limits heat transfer. At high RE, turbulent flow increases the Knox number, improving the cooling efficiency. Using dimensionless analysis, engineers can study how variables like tube size, cooling velocity, and surface area affect performance. Comparing dimensionless number helps predict how different designs perform even before prototyping. By optimizing this parameter, we can design radiators that are compact, lightweight, and fuel efficient, while still keeping the engine cool and reliable. Dimensional analysis helps engineers make sense of complex heat transfer systems by reducing them to just a few dimensionless numbers. With tools like a Buckham-P theorem, we can better understand, design, and optimizing systems like radiator, where performance, space, and efficiency all matter. Whether it's improving engine cooling, or design next-gen heat exchanger, these concepts are essential in creating smarter and more sustainable engineering solutions. So, that's all for me. Thank you.